Hello everyone, welcome to GChem classes. So today we are going to discuss for molecular orbital picture. So today that we are discussing for IIT-JAM, right? So you have exam on like February 2nd week, Sunday. So important concept I am discussing. So which can be the probable concept for your upcoming examination, right? So do what that go through with these concepts and then try to solve those PYQs. If it is if you are able to solve those PYQs based on this concept, then it will be help you out in your examination too, right? So let's see today what we are going to discuss it. We are going to discuss it for MO diagram. Okay. So for MO diagram, first we are going to take it for homo. Okay. Diatomic. Okay. Homonuclear diatomic. Right. So homonuclear diatomic we are going to discuss it. Suppose first one we are taking H2. For H2 molecule we will take it. So what will be the MO diagram for H2? What will be the HOMO? What will be the LUMO? Okay. So whether they will whether the molecule H2 is existing or not. Okay. What is the bond order? Everything we will come to know by this MO diagram, right? So for H2 we know that for hydrogen it will be 1s1. So another hydrogen also it is 1s1, right? So how we are going to make this MO diagram? We'll put this hydrogen this side and this one is this side, and we know that its atomic orbital it is 1s1. Here also for this hydrogen the atomic orbital is 1s1. So what will happen? This is bonding molecular orbital, this is anti-bonding molecular orbital, right? So just we need to draw this. Okay, so this we call BMO, bonding molecular orbital, right? And this is ABMO, anti-bonding molecular orbital, right? This one is sigma 1s. Okay, this will be sigma star 1s. Okay, this is high energy and this is anti-bonding. This is in lower energy and it is bonding. So what all a concept we will come to know with this MO diagram? Let me discuss. This is atomic orbital, right? What is this? This is atomic orbital of one hydrogen. This is atomic orbital of another hydrogen, correct? Now what is happening? This will be your energy diagram or energy way of energy, like from down to top. It is going this energy. So what is happening? See, if you just extend this BMO, bonding molecular orbital, this will be your energy 1. And then for atomic orbital, if you are extending till here, so what will happen? This will be your atomic orbital's energy and this will be your anti-bonding molecular orbital energy, correct? So now what all you will come to know with this? So the bonding molecular orbital's energy is lesser than your atomic orbital energy, right? So whatever atomic orbital's energy is there, so when this is forming a bond, like individual hydrogen, it will be in higher energy. When it will form the bond like H2 molecule, then what will happen? The bond energy, like the energy of the molecule, the bond, it will be decreasing. So we know that the lower the energy, the more stable the molecule, right? So now we can say, so 1s1, so one electron will be here for this atomic orbital. For this hydrogen, here also one atom will be there. Now what is happening? This will together form a bond. So we know that each bond will have 2 electrons, correct? So now one electron will come from here, another electron will come from here. So now this is a bond, right? So how we are going to calculate that how many bonds are there between the hydrogen? So what we are going to do is bond order. So how you are going to calculate bond order? It will be number of electron in bonding molecular orbital, okay, minus number of electron in anti-bonding molecular orbital divided by 2. Okay, what is NB? Number of electron in bonding molecular orbital. What is Na? Number of electron in anti-bonding molecular orbital, correct? Now just put the values. See, in BMO we have only 2 electrons, so we just put it 2. Minus in anti-bonding we don't have any electron, right? So we have to put 0 divided by 2. How much it is coming? 2 by 2 means 1. So now we came to know that between the hydrogen there is only one bond, okay, and the molecule hydrogen is existing. Okay, what is the HOMO for this hydrogen? This one is the HOMO. highest occupied molecular orbital is sigma 1s, right? And what is the LUMO? LUMO will be sigma star 1s, right? Lowest unoccupied molecular orbital. This is the LUMO. So likewise, many things will come to know with this MO diagram, right? Where whatever molecule they will ask, the bond order they will ask the stability, they will ask the whether between the hydrogen it is sigma bond or pi bond. Let's see, it is one sigma 1s. Okay, sigma 1s. It means this bond is sigma bond. Correct? This bond is sigma bond. So many informations will be available based on this. So next we'll be discussing about helium. Okay. So I'll also draw it here, and meanwhile what you do it, you also try to do by yourself and tell me whether helium 2 is existing or not. Okay. This helium 2, whether it is existing or not. What will be the bond order? What is the LUMO for this? Okay. And what is the HOMO for this? Correct? I'm rubbing the board. Meanwhile, you just try to make the helium 2 molecular diagram, right? So, helium 2. Maybe you are making. So, for helium, what will be the electronic configuration? 1s2, right? So, now you see, here one helium, here one helium. We know these are the atomic orbitals of helium. 1s2, here also 1s2. So 1, 2, 1, 2. Now we know that this is BMO, bonding molecular orbital. This is ABMO, anti-bonding molecular orbitals. Now we have 2 to 4 electrons. We have to fill those 4 electrons, and we know that for each and every orbital we can fill only maximum 2 electrons. We can fill it up, right, in each and every orbital. So this is one orbital. So 1 electron, 2 electron. Total we have to fill up 4 electrons. So 2 electron already done. Remaining is 2 electron, right? So remaining 2 will be 1, 2. So now you just see what will be the bond order for this molecule. Number of electron in bonding minus number of electron in anti-bonding divided by 2, right? So what will be the number of electron in bonding? It will be 2 minus what will be the electron in the anti-bonding side? It is 2 divided by 2, right? So it will be 0 over 2, total 0, right? The bond order is 0. Bond order means how many bonds are there in between those two atomic orbitals, right? So how many bonds are there? 0 bonds. It means helium 2 doesn't exist. Correct? Helium 2 doesn't exist. Okay? So likewise we have to calculate. Correct? So now after this helium, we'll go for lithium. So we'll see the homonuclear diatomic first, and then we'll go to heteronuclear diatomic, then we'll go to polyatomic. Okay? Polyatomic amount also we will discuss it, like carbon dioxide, like water, H2O, like BeH2, NO2, okay, everything we will discuss it. So next will be lithium 2. Whether this molecule is existing or not, let's try by yourself and let me know in comment section, correct? So in this we know that lithium, it will be 1s2, 2s1, correct? Now just do it. So we are not going to make for this 1s2. Why? Because 1s2 and 1s2, that bonding and anti-bonding will get cancelled. I'll do it now. The next time onwards, I will not do for the completely filled up orbitals, right? So what I'll do, for this I'm doing, this side also lithium, this side also lithium. This is 1s2, this is also 1s2, this is 2s1, this is 2s1, okay. Now what is happening? For this is bonding, this is anti-bonding. Okay, we have here 2 electrons. So total 4 electrons is there. 1, 2, 3, 4. So this is bonding molecular orbital. This is anti-bonding molecular orbital. For this will be bonding. This is anti-bonding. So here also it is BMO, bonding molecular orbital. This is anti-bonding molecular orbital. And we know that lithium last 2s1. So 2s1, 1 electron, here also 1 electron. So what is happening? These 2 electron we have to fill it up, right? So 2 electron we are going to fill it up. See, 1, 2. So 2, now we can't fill up here. So now how this molecular orbital it will be named? It will be 1 sigma 1s2. This will be sigma star 1s2. This will be sigma 2s2. This will be sigma star 2s2. Okay. Now if they are asking that what will be the molecular configuration, how you are going to write it for this lithium 2 plus molecular configuration? So lithium 2, it will be sigma 1s2, then sigma star 1s2, then sigma 2s2. Okay, then if you want to write, you can write it, but you have to mention it sigma star 0. You have to mention it 0, then only you are supposed to write this. Otherwise, till here you write it. Okay, leave this one, not required, because it is a 0, right? Why you will write it? So this will be the molecular configuration, right? Now our job is to find bond order, right? So just do it bond order. If you are just see how many numbers of bonding electron minus how many numbers of anti-bonding electron divided by 2. So if you are counting from here, so bonding will be 2 plus 2. Total it will be 4 minus anti-bonding, only 2 are there, okay? Here 0. So 2 divided by 2. How much it is coming? 2 by 2, it will be 1, right? Suppose here also 2 is there, bonding molecular orbital, anti-bonding molecular orbital is also having 2. So what we are going to do is just cancel it out, okay? Because don't make things complicated, because we know that if it is this orbital is filled, totally filled, then bonding and anti-bonding will be also filled up, right? And then finally it will be 0. So better to avoid the complication, just we will neglect it, okay? This down, whatever is there, that will be neglected. So only one picture we will take it, and then based on that we will just calculate it. See, for now, for this MO diagram, how much it is coming? So it will be bond order equal to number of bonding is 2 minus anti-bonding is 0 divided by 2. It will come 2 by 2 and it will be 1. So number won't be changed there, correct? So now bond order is 1, means lithium and lithium, in between lithium only one bond is there. And that, what is the nature of this bond? You just see it is in sigma 2s2, right? So it means this bond nature is sigma bond. Correct? Homo and LUMO, you can find it out easily. This will be HOMO, this will be LUMO, right? Highest occupied molecular orbital, lowest unoccupied molecular orbital, correct? Likewise, you can calculate it. So lithium, after lithium, we'll do it for beryllium. Okay, let's see. For beryllium, suppose today time is not permitting, next time we will discuss the problems, okay? In 2019, I guess 4 or 5 questions they have asked based on molecular diagram, okay? And 2022 also they have asked 2 or 3 questions based on molecular diagram, right? These are the sure short questions and very easy concept is there. So please do revise this topic, okay? And whatever I am giving here, that much is enough for molecular orbital, and please believe me that you won't whatever you are learning here, with that only you can solve it, whatever molecular diagram questions they are going to ask you in examination, correct? Just try it, you will be surprised. So now be the beryllium 2, right? Be2 molecule. So how you are going to draw the molecular diagram for this? So beryllium, how much it is coming? Beryllium, what will be the electronic configuration? 1s2, 2s2, right? So second beryllium also the same configuration will be there. Just we will take the outer one, the 1s. This one I am not going to take it. Only this one I will take it. So this will be 2s2. Here also I will put 2s2. Now see, this is the bonding molecular orbital, and this one is anti-bonding molecular orbital. Correct? So how much we have? 2 electron, 4 electron. Total 2 plus 2, 4 electron I am having. So it will be 1, 2, 3, 4. Correct? What is the name of this molecular orbital? It will be sigma 2s2. This will be sigma star 2s2. Now bond order. Okay, bond order equal to number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital divided by 2. So how much it is coming for bonding? It will be 2. Anti-bonding it is 2 divided by 2. So total it will be 0. That means this beryllium 2 is not existing. This molecule is not existing. Beryllium 2 is not existing. Correct? Because bond order is 0. Correct? So next we will take it after beryllium. What is coming? Boron. Let's see. One more concept we will learn it when we will like before boron. Just before boron we will see that the concept is called S and P mixing. Okay, S and P mixing. Okay, S orbital and P orbital mixing. What is this sp mixing? See, if s orbital and p, if energy gap is lesser, then what it will happen? It will mix up. If the separation is more, s and p, then what will happen? That mix up will not take place. Correct? Let's see. This is for boron. This is carbon. This is nitrogen. This is oxygen. This is fluorine. Let's see how it will work. This is s orbital. Okay, and this one will be p orbital. Correct? So now for boron, here is the s and here is the p. And what is this one? This is energy separation. Okay, this will be energy separation. So now their energy gap is minimum, right? So easily here mix up can be done. For carbon, here is the s and p will be little bit far away. For nitrogen, here is the s and p will be little bit far away. For oxygen, here is the s and p will be little bit far away. For fluorine also same thing will happen. So what is this energy gap and what is the sp mixing? We'll come to know now. These two energy gap is very less. What will happen? This mixing will take place and what will happen? This 2px and 2py will come down and 2pz will go up in molecular orbital diagram like this. Okay. Because of this sp mixing, what is happening? This sigma 2pz will go up and this pi 2px and pi 2py will be in down, right? This will be having lesser energy compared to your sigma bond. Okay. Always we used to see that pi bond will having a higher energy compared to sigma bond, right? But if sp mixing is happening, then what will happen? This pi bond will have the lesser energy than this sigma bond, right? Here also the same thing. Just this will in this place the continuity will break. Correct? Till this nitrogen, this sp mixing will be taking place. After nitrogen, the energy gap is so high that this mixing up can't be take place. Okay. Then what will happen? This is the atomic orbital. This is the atomic orbital of oxygen. What will happen? This sigma will be in lesser energy. Okay, sigma pz, 2pz, you write it. Then this will be the pi. It will be pi 2px and it will be pi 2py. Correct? So see here due to this sp mixing, pi energy is lesser than sigma, and here the sp mixing is absent. Because of that, this sigma energy is lesser than pi. So till nitrogen this will follow. After nitrogen, oxygen, fluorine, bromine, iodine, whatever is there, everywhere this molecular configuration will be there, where the sigma bond will be having lesser energy compared to pi bond, right? This thing you just do practice by yourself, or if you want to take a screenshot, you can take it. I will be out of frame. Correct? Okay. Now we are going to solve it. So for boron, for carbon, for nitrogen, because in examination they will directly ask in B2 molecule the nature of that bond. Okay. So that thing also we have to learn it here. And okay, let's see. For boron molecule, right? If you have any type of doubt, you can directly WhatsApp me and you can ask me, right? I will solve it. Okay? Any kind of doubt if you have. So for boron molecule, we will see it. So boron, let's see. This will be 2p1. Here also 2p1. Okay, this is a boron. This one is also boron. Boron, what is the electronic configuration? Just write it down. 1s2, 2s2, 2p1. So this we know that it will be 0. So only 2p1 we are going to take it. So 1 electron here, 1 electron is here. So now we have to see here sp mixing is taking place. Okay. So here what will happen? Upper side there won't be any change. Okay, upper side this will be pi star will come first, then sigma. So how this you are going to name it? Pi 2px, here it will be pi 2py, here it will be sigma 2pz. This one pi star 2px, this will be pi star 2py, this will be sigma star 2pz. Correct? So now you have two electron you have. Now what will happen? One electron is here. You can't put the second electron here because these are the same energy level, right? So in that same energy level, what you have to do it? One electron will be here. First this orbital will get one electron, then only pairing up will start, right? So second electron will be here. Now you see whether B2 molecule is paramagnetic or diamagnetic. It is paramagnetic. That will be the magnetic properties. So how you are coming to got to know? Because of this MO diagram, right? If you are don't aware about this sp mixing, what you are going to do is this sigma bond will be in down. If you are putting sigma bond in down, so both the electron will filled up in a single orbital, and what will happen, this will be show as a diamagnetic, and that is wrong, right? So now you come to, now we will see bond order. What will be the bond order here? Number of electron in bonding molecular orbital minus number of electron in anti-bonding electron orbital divided by 2. So how much it is coming? Bonding, it is 2, minus here it is 0 divided by 2, so it will be 2 by 2, it is 1, right? This one is 1, correct? Now what is happening? Just we have to see what is the nature of this bond, this boron and boron. What is the nature of this bond? You see where it is in pi, right? So the nature of this bond is pi bond. Don't say this is a sigma bond, right? It is not a sigma bond, it's a pi bond, correct? It's a pi bond. But while seeing one single bond, you might be saying that this is a sigma bond, but this is not a sigma bond, this is pi bond. And why this is pi bond? Because due to sp mixing, the pi energy is lesser than sigma, so electron will fill up first in pi, then it will go to the sigma, correct? So what else we can learn it here? This will be HOMO. This sigma 2pz will be LUMO. Okay, what else we will get to know from here? These are the unpaired electrons, so this magnetic nature is paramagnetic. Okay, likewise you can say, okay. So next molecule we will see, let's see what is the next molecule after boron. It will be carbon, right? In carbon also you will get to surprise. Till now what you know that carbon, okay, how many bonds will be there in C2 molecule? How many bonds will be there? If you know the number of bonds, then next question will arise, what is the nature of those bonds, whether it's a sigma bond or pi bond, or maybe one is sigma, one is pi. Answer it, okay, in comment section. By the time I will draw it for C2 molecule. So for one carbon, what is the electronic configuration? 1s2, 2s2, 2p2. Now we are going to focus on 2p2 because we know that these will be the cancel out and it will be 0, right? So just draw it for 2p. So here one carbon, here is also one carbon, and this will be the atomic orbital. This also atomic orbital for carbon. Now just fill it up. How many are there? 2. 1, 2. Here also 1, 2. Now this is your pi 2px. This one will be pi 2py. This is sigma 2pz. This will be pi star 2px. This will be pi star 2py. This will be sigma star 2pz. Correct? Now you have to fill it up 2 to 4 electron, right? So 1, 2, 3, 4. Everything is got over in pi itself. Now bond order. What will be the bond order here? Bond order is number of electron in bonding molecular orbital. How many are there? 4. So 4 minus number of electron in anti-bonding. How many are there? 0. So put it 0. How much it is coming? It will be 4 by 2 means 2. So now what is the nature of those two bonds, right? We know that carbon and carbon, it is double bond, right? Now what is the nature of these bonds? Both the bonds are pi bonds. This is also a pi bond, this is also a pi bond. There is no sigma bond in carbon 2. See, this is also in pi, this is also in pi. So both are pi bond. we don't have any sigma bond in C2. So B2 also we have pi bond, but one pi bond. C2 also we have pi bond, but two pi bond, not single pi bond. Or you can't say one sigma and one pi. And now the next question is, what is the magnetic property of this C2? What is the magnetic property of this C2? It's a paired dot, right? So it will be diamagnetic. Correct? It's a diamagnetic. The magnetic properties of C2 is diamagnetic. So next will be our nitrogen. Correct? Let's see for nitrogen. I'll not rub this one. I'll just rub this electron. Okay. So I can use shortcut, right? But you don't use any shortcut. We are working for nitrogen. Let's see. N2 molecule. We know that electronic configuration of nitrogen is 1s2, 2s2, 2p3. So now one more electron here, one more electron here. Same thing will be there because sp mixing is still persisting because the energy gap between 2s and 2p is lesser. Okay. So now 336 electron is there. So 1, 2, 3, 4, 5, 6. Okay. So now what is the bond order? Number of electron in bonding molecular orbital is 6. 6 minus number of electron in anti-bonding is 0. Put it 0 divided by 2. So it will be 6 by 2, 3. So bond order is 3. It means that nitrogen, in between these two nitrogen, there will be 3 bonds. So what is the nature of these bonds? We know that one is sigma. See, this is sigma 2pz, right? This bond belongs to sigma. This belongs to pi. And this is also belongs to pi. So one sigma and 2 pi bonds. Okay, one sigma and 2 pi bonds are there in N2. Correct? Okay, next is O2. We'll just see for O2. This O2 we will see it where the sp mixing will not taking place. Okay. So first example, after a long we will see where the sp mixing will not take place because S and P energy gap is higher. Right. So here 1s2 for oxygen, 1s2, 2s2, 2p4. So we are just discussing about 2p4. Okay, remaining we know that it will be 0, right? Oxygen, atomic orbital, here also atomic orbital, 1, 2, 3, 4. 1, 2, 3, 4. Okay, 2p4. Now what is happening? Here sp mixing won't be there. So sigma will be in lesser energy. Okay, then pi will have the energy. Here also then pi star, then sigma star. Okay, this will be your sigma 2pz, this will be pi 2px, pi 2py, pi star 2py or x, whatever you want, pi star 2py, here sigma star 2pz. Now we have 4, 4, 8 electron. We have to fill it up this 8 electron. How? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now what is the bond order? Bond order is number of electron in bonding molecular orbital is 6 minus number of electron in anti-bonding is 2. So it will be 4 by 2, 2. So the bond order is 2. So in between oxygen there is 2 bonds. And what is the nature of these 2 bonds? One will be sigma bond and one will be pi bond. Okay. Now question will arise in your mind. Here one pi bond, here one pi bond, right? This is pi bond. This is also pi bond and this is sigma bond, correct? Now you just see, this is anti-bonding and anti means it will just do the negative. So we have overall, just we will see, we have one sigma bond plus we have 2 pi bond. Okay, minus in sigma there is no electron. So 0 sigma plus 1 pi bond is there, right? Together 1 pi bond is there. So minus 1 pi bond. Overall, how much it is coming? This will be 1 sigma because 1 minus 0 is 1 plus 2 minus 1 is 1 pi. So how much it is coming? 1 sigma and 1 pi. So see, 1 sigma and 1 pi. Okay, this is your answer. Correct? So what is happening? If they are saying that 1 sigma and 2 pi we have, so here the electrons, anti-bonding electrons are in pi star, right? So what it will be? The reduction will take place where it will be in pi bonds, right? So likewise we are solving this. Okay, so I think Next class we will just discuss it for F2, and then we will start for heteroatomic molecules, and then heteronuclear diatomic molecules, and then polyatomic molecules, and we will start discussing these questions from previous year. Okay, so thank you for watching. Thank you very much.